Hey guys, welcome to Tutes Online. Today I'll be talking about logarithms and exponents. We'll start by talking about some terminology. So for exponentials, the terminology for this function would be that a is equal to the base and b would be the power or index. For logarithms you can have just log a, and when there's nothing here, when there's no number here, it's assumed that it's 10. Sometimes you will have a number written there, so it could be log 2a. So here we have our base equal to 2. Sometimes, however, it could be a natural log, and that's ln a. And for this case, the base is equal to Euler's number, which is 2.7, etc. We'll now look at some laws. So for exponentials, if we had a to the b times by a to the c, this would be equal to a to the b plus c. So a times here just turns to a plus. For logarithms, there's a similar concept. Log to the base a of x, y, this would be the same as log to the base a x plus log to the base a y. And similarly, if we had a to the b divided by a to the c, this would be a to the b minus c. Or for logarithms, if we had log a x over y, this would be log a x minus log a y. For exponentials, if we had a to the b to the power of c, this would be a to the power of bc. Similarly, for logarithms, if we had log to the base a of x to the power of b, this could be written as b. You bring the b down to the front, and then you just write log to the base a of x. So the b, which was the index, got brought down to the front. Also, if we have a to the power of 0, or anything to the power of 0, this is 1. Or a to the power of 1 is just a, the original value. For a logarithm, there is log to the base a of a, and this is just equal to 1. Also, log to the base a of 1 is equal to 0. So that's a few laws when you're using exponentials or logarithms. But what does a logarithm actually mean? So if you had the example log to the base 2 of 16, what this is asking is how many 2's, which is our base, do you need to times by, so what value of n we're looking for, to get to our value here, 16. So what we're really trying to find here is what n is. But for this one, we know 2 to the power of 4 is 16, which is 2 times by 2 times by 2 times by 2. So we get a nice easy number, which is n equals 4. You might want to check some answers when you're working with logarithms, but if you look at your calculator, there is no log to the base of 2. There's usually only a log, or log 10 as it is, or a ln, which is log to the base e. So for this you have to use something known as the change of base formula. So if you want to solve something like log to the base a of x, you would have to put into the calculator ln x ln a. So your x goes here on the top, and your base goes into the denominator. So if you put in that previous example, which is log to the base 2 of 16, this would be ln 16 over ln 2, which should give you the number 4. So this formula is very useful to know. If you want to solve something like 3 to the power of x equals 16, for example, you know that you can take the natural log of both sides. So this is ln of 3x equals ln of 16. So it's important to do it to both sides. Just like if you times both sides by 2, that would still be a valid statement. So we know from the previous laws that this here could be brought down to the front. So this would be x times by ln 3 equals ln 16. And so our x value would be equal to ln 16 over ln 3. And if you put that into a calculator, you get about 2.52. Log laws is also useful if you see something like ln of 4e equals 1 plus ln 4. So this makes sense because we know that if you're timesing two values here, this is the equivalent of adding. So this could be ln of 4 plus ln e. We know this natural log is log to the base e. So what we're asking is e to the power of what equals e. We know that that's e to the power of 1. So therefore, this value here is actually equal to 1. So we have ln 4 plus 1, which is our value here. So as well as being lots of fun, exponentials and logarithms are very useful in science. So you'll find things like a bouncy ball will have an exponential decay in height, populations have exponential growth, and exponentials are very useful for calculating the half-life of objects. So if say we found a skull and it had 20% of its carbon-14 that it should usually have. Because carbon-14 is a radioactive isotope of carbon, it decays. So from this, we can figure out how old the skull is. We know that the amount of carbon-14, xt, which is dependent on time, would be equal to its initial value, which is how much carbon-14 it had originally, but now it has 20% of that value. And this 20% is a result of the half-life. So the half-life, which is an exponential decay. This is time divided by the half-life of carbon-14. And the half-life of carbon-14 is 5,730 years. So we put that in here. So at the point at which t, time, equals 5,730, this will be 5,730 over 5,730, which is 1, which is 0.5. So it has half the amount left of the carbon-14. So now we have an exponential to solve. So if we take the natural log of both sides, that's ln of 0.2 equals the natural log of 0.5 to the power of t over 5730. Everything as an index can be brought down to the front, so this is t over 5730 times by the natural log of 0.5. So rearranging for t, so times this over here, divide this over here, you have t equals 5730 times by ln 0.2 over ln 0.5. And that's equal to 13305. And the units for this is years because we used 5730, the half-life, in years. So this is years. So that's how we use logarithms and exponentials to solve problems in science and also in mathematics. I hope you enjoyed the video. Please comment if you have any questions, check out the website, or subscribe to the channel. Thanks.